120 beats per minute. Okay, now we're going to do the same thing at 250 beats per minute, the highest rating for cakewalk.
Period, we'd like to show you a demo using first the keyboard and then the computer. Ryan's hooking up the MIDI cable from the computer now. Turn the power on. And all right, La.
Good morning. Welcome to this session. This is the Electrical and Computer Engineering session of the Senior Design Projects Presentation Conference. My name is John Casey. I'm a faculty member in that department and chair of this particular session. Our next presentation is entitled The Drum Emulator, and our presenters are Ryan Giorio, Chong Wei, and David Stoll. Gentlemen.
Hello, ladies and gentlemen. My name is Ryan Giorio, and my team members are Chong Hin and David Stoll, and our faculty advisor is Dr. Fred Severance. And our sponsor is the band Love Hammer, and today we're going to be talking about the drummer emulator. Why a drummer emulator? Well, in the music industry, you basically have two options. One, you can find a real drummer and hope that he's talented enough to play the drums for the songs that you like, and hope that he's reliable enough to show up on time in practice. That was the first one. The second one, it's great to feel live drums, real drums for a live show. This means basically when you play with synthesized drums at a concert, you can hear them fine when you're in the audience. But when the band's playing at a live show, they need a PA or monitor to feed them the drums. And sometimes clubs don't have the drum or the monitor, or they're hard to hear. And the drums are essential for everybody in the band. You know, the guitarist, the bass player, the singer to keep rhythm. It can also be used in for a recording engineer in a studio environment. This is if if the drummer come in, had a bad session, they wanted to replace his stop, they could come in or put his tone in a particular spot in the song. Who's who and what's what? The drummer emulator. Mr. Ooi Chong Hin is going to come up and talk about the controller circuit and the flute chip. I'm going to talk about the power circuit and the actuator. And David Stoll is going to talk about the specifications and economic analysis. And then the team's going to get together and do a little demonstration and take some questions. Okay? I'm going to bring Mr. Ooi out to talk about his controller circuit.
Good morning, ladies and gentlemen. I shall be talking about the control circuit. Before I do that, let me give you all a brief introduction to MIDI. MIDI stands for Music Instrument Digital Interface, and it's the standard protocol used in the music industry to communicate between musical instruments. MIDI transfers at a rate of 31,450 bits per second with tolerance of plus minus 1. Is sent serially. Data that's being sent through MIDI lines are just ones and zeros, and it's the grouping of these ones and zeros that give definition to MIDI. The way this group works, the way these data bits are grouped are what defines the MIDI messages. An example of MIDI messages are node on, channel number, velocity, pressure, channel after touch, and pitch. For our project, we will be looking at the node on, channel number, velocity, and note value. Here's an example of a file created by a popular music software, Cakewalk. These are, over here we have the text equivalent of the binaries that will be sent through the line. We have three values that we're looking for right here. And we have the same values that are sitting right here. And these are the node on, channel number, and node values that will be sent through the line that we are looking for. Moving on to the control circuit, we have the input, the MIDI input, that we send into the optocoupler. The optocoupler is used to isolate the controller circuit from the expensive MIDI devices. The isolated signal is then sent into the pitch chip, which will decide what to do with this signal. Here we use an external oscillator. Even though the pitch chip has an internal oscillator, but since it has a fair use tolerance of up to 28%. Therefore, it is necessary to use a ceramic resonator or a crystal for high-speed transmission, such as our application. Here's a picture of circuit on the breadboard. The MIDI input port, the opto isolator, the crystal, and the picture. And one more picture. This is the computer board etched out. As the bottom of the board is the top of the board, we have two sets on one board. Moving on to the picture. Here's the block diagram of the picture. At the beginning of the code simply reads 8 bits of data. This part of the code was pre-written and is available from Parallax. Once it has read the 8 bits, it then scans through the bits for the desired node on, channel number, and node value. These values have been hard-coded into the chip. Further expansion, we have the ability to change these values by using an LCD and a numeric keypad. Once it has matched the desired node on, channel number, and node value, it then looks for the velocity. The velocity immediately follows after the note value. Once it has detected the velocity, it will then match up its figure against an on-time table. What is an on-time table? An on-time is simply the length of time a signal is sent throughout the output of the picture. The signal is then sent into the power circuit, which Ryan here will now talk to you about.
Okay, before we get to the power circuit, I'll give you we were trying to keep an actuator, so we decided to go with the solenoid. It has 4 basic parts here. It has the a spring, a stator, the coil, and the plunger. How it works is we put a voltage across the inductor, or the solenoid. It creates an electromagnetic field across the solenoid, and it causes the current to be forced into the coil. The current has direction. You place your fingers in the direction of the current. It shows you the direction of the electromagnetic flux, and that causes the plunger to move. The solenoid can be represented by the solenoid equivalent circuit, which is an inductor value, and a resistance value, which indicates the resistance of the coil in the solenoid. And here's the drummer emulator, complete schematic. As you can see here, this is when Mr. Ooi was speaking about the output coupler of the crystal. And then here's his output pulse to our solid-state relay. It basically works like a DC switch. And when the voltage comes on high from his picture, the logic high, the solenoid is actuated, and when the signal goes low, it turns off. Here's our DC source, and our 2 diodes. That's our snubber circuit to protect our solid-state relay from any counter EMF that may occur from the inductive load. Here's our 5-volt power supply. This is for the controller circuit, and we put a 12-volt supply in here for our fans. It's for some heat columns. We have some counter for heat column in the power supply, and the switching box, which I'll get to next. And this is our 60-volt power supply. And here's our switching box. I don't think you can see if there's a fan right there. It's powered by that 12 volts also. Here's our solid-state relays and our snubber circuit. And as you can see, there's a lot of room in here. There's enough room for 16 different actuators to be added on for this total. We have 2 on it right now. And we had to determine the on time in order to get the correct decibel levels for this particular system. Here you recommend our power circuit, and what we did is we used a 555 timer to determine the time. This is an ostable, which means it has 2 states, 0 volts for low and 5 volts for high, and neither one of them is stable, constantly pulses. And R2 is fluctuate. You adjust R2 in order to get your specific on time, and then you use a decibel meter and read your decibel meter at this particular R, and then you get you calculate your on time. Here's the formulas for the 555 timer that we use. This is our T low and T high logic in seconds, and then this is our period. And our duty cycle is the T high divided by the period. And here's an example of one of the experiments that was done, part of the experiment. And this duty cycle ended up being about 0.66 milliseconds, or 0.66%. Here we see the typical cycle for the 555 timer. You can see the period is 0.125 seconds, and the on time is, this is 5 milliseconds, and this duty cycle is about 4%. And this just keeps repeating for 8 times per second. And here's some typical values for decibel values for some typical sources. As you can see, at 60 dBs, it's typical conversation. At 90 dBs, it's some type of traffic. At 100, it's a lot of classical music. And at 120, it's about the level of rock music. And here's a graph of our on times versus our decibel levels. As you can see here, our minimum value is 87 decibel levels. It's a little bit below heavy street traffic. And here's 100 dBs. That's a lot of classical music. And in our saturation region, we have 113, which is pretty close to rock music. And now I'm going to turn it over to Mr. David Stoll to talk about our specifications and economic analysis.
The drummer emulator has a number of specifications which we've broken down into three parts: requirements, preferences, and goals. The drummer emulator is able to accept MIDI signals coming from any source and is completely MIDI compatible. It's also portable and is able to be mounted on any size drum set. Partway through the semester, it was decided that we use 25-pin RS-232 connectors instead of the quarter-inch jacks, and that was because that way all MIDI signals and power signals could be contained in one cable. We also have a drum stimulating device, and as Ryan said, it's a solenoid. We were also able to successfully meet response time, decibel levels, and cycle requirements. The cycle that we achieved was consistently 10 beats per second and better. The drummer emulator is also easily repaired and expanded. We have, our base unit has 2 solenoids, and any future additions will be able to use the existing power supply. You'll notice that we were unable to meet our $1,500 preferred cost limit, and I will talk about that further in detail in the next slide. At this point, the drummer emulator is not ready for manufacture, but we feel that because we have a working system, that Love Hammer will be able to follow up on that very easily. First thing you'll notice is the total cost at the bottom. We're approximately $133 over the preferred cost limit. The main reason for this is that Love Hammer not only wants a project that sounds good and works well, but they also would like one that looks nice during their live sessions. The main reason for that, for the cost, is the enclosures. We decided to spend a little extra money on the enclosures to get that nice aesthetic look to them. You'll notice that a number of these components have stars next to them, and these are the ones that need to be purchased if additional striking units are added to the system. The approximate total cost of any additions will be $600. Love Hammer will be using the drummer emulator in future studio recordings, and we'll also be using the expandability features to connect the drummer emulator to an entire drum set. The project gives an alternative to supplementing a human drummer, and although a human can never be replaced, it does give a less effective yet adequate replacement. As technology advances, the drummer emulator can be continuously improved to shrink the gap between man and machine. And before we move on to the demonstration, we'd like to say a few thanks to some people that helped us throughout the semester. First of all, Dr. Greenwood, I don't see him here, but he helped us with the flow chart. And Dr. Kelman for all of his help with the power electronics. Appreciate that. Stephanie Tanner for her help with the presentation and travel assistance. Mr. Peter Giorio for his help with the enclosure design. And of course, Dr. Severance for all of his help this semester and last with his advising help. At this point, we'd like to give a demonstration of our project with both a keyboard and the computer. As we're setting up, this is actually what will be played. First we'll be using a keyboard, and it's touch sensitive, so you'll notice the solenoids respond appropriately. Now we'll disconnect the keyboard and connect the computer to it. We'll be playing this tune twice, once at 120 beats per minute, and then again increasing that, almost doubling it, or more than doubling it to 250 beats per minute. Now we'll double that tempo. We'd like to ask if there are any questions.
Have you actually measured the rate, motion, of the plunger and the solenoid? In other words, you set a frequency in the program, correct? And therefore, how do you know that you're getting actually that frequency out there? You use a recording, maybe a microphone?
To record the decibel level? Is that what you're getting at?
Not the dB level, but the actual rate.
Oh, the frequency?
Yeah.
Oh, yeah, I set up the 5x5 timer. I actually set it up for the frequency, for those frequencies, like 8 hertz, 6 hertz, 10 hertz, in order to, and for a certain decibel level, like 106, that's dBs. I set the on time for that after I'd already determined it. And then I set the period for that length of time, and then I repeated it.
But how do you know you're actually getting that? Have you tested for that, is my question.
No, as far as, are we getting that? As
Yeah.
far as,
The actual rate, frequency.
did we actually record it and to make sure that we got 8 times in a second, like video games?
Yes.
No, we didn't do that.
I understand, first of all, you're varying intensity by modulating your duty cycle, is that correct?
No, we're changing our decibel level by modulating our on time.
Okay. But you're varying your duty cycle. That was what the 555 timer section, you don't have a 555 timer in there. You're trying to find out how long to make your duty cycle in order to get a certain intensity.
Well, I really wasn't concerned with the duty cycle at first. What I wanted to do was determine the on time. And what I did was I set up a 3-second interval so that I could just get one beat. And then I changed it until I got the required decibel level that I wanted.
Well, tell me, how are you modulating intensity? Strength of strike. How do you do it? What do you modulate in?
You actually change the on time.
Okay, so you're using pulse width modulation for duty cycle modulation.
Right.
Okay, that's what you're doing. Okay. Now, where do you pick that up out of the MIDI signal?
When you hit the key,
Yeah.
at different pressures, when you hit the key, a different signal is sent. So every time, that's when the velocity comes in. When you hit, let's say, when you tap the key, velocity of, let's say, 20 comes in.
Okay, so velocity carries the intensity. The velocity bit in your MIDI signal.
Right.
Okay. Now, how did you measure the intensity level? Did you actually have a dBE? Okay. And in this case, what kind of meter was it? Was it a peak capturing meter?
Yeah, that's what I went for the peak capture.
Okay, so you did a peak capturing. And then, okay, I understand. And what was your maximum? You got up to 10 beats per second.
Right.
Okay, I'm very impressed. Good job. Thank you.